It's called the principle of equivalence. Okay, so far, the underlying assumption is that you know special relativity. And now you should really know special relativity. The second problem set is already on the course's webpage. Okay, so now we're going to assess what doesn't special relativity have? Gravity. Now we're going to do gravity. And basically there are two questions that we want to answer. Okay. The first question is, okay, the whole concept of gravity, what is it? What is the difference between Einstein and Newton? Okay. Should have gotten that from the introduction part, just to be sure.
General gravity, according to general relativity, is a geometry, not a force.
Right, right. Gravity is not a force, gravity is a geometry. Namely, the space-time is curved, it's not flat. So that raises two questions, two fundamental questions, which are what? One, how does the existence of mass or energy, because E is equal to mc squared, how does that act to curve space-time? Gravity is geometry. Question number one, how does the existence of matter or energy act to curve space-time? The answer to that, you know, it's in Einstein's equation, and we're going to take us about half of the semester to derive it. The answer is Einstein's equation. And Einstein's field equation. The second question is, okay, if we accept the idea that space-time is curved, how do we describe the motion of particles in a curved space-time such that we say, we don't know in relativity, right? What do we say? That they are subject to gravitational force, namely accelerating. That, in fact, is a much easier question to answer. So we're going to start actually answering this question. So how do particles, but here when I say particles, I also mean massless particles, namely photons, including photons or massless. Travel in curved space-time such that we call their trajectories being influenced by gravity. These are the two fundamental questions that this concept introduces. And as I said, we're going to spend half the semester getting that. Second half is solving them. But today we're going to start with actually answering the second question, because it's much easier to answer. What's the experimental basis here for that? You should have seen that in the introductory part, and it was made of it. What is the experimental basis?
basis of what?
Well, the whole concept, really, actually.
And the delay of the ones.
No. I didn't get it.
Propagation of light.
No.
Imagine.
Maybe we should spend more time on that. But Vosh's experiment. Experiment. What is a Vosh experiment?
Understand if
It balances the effects of acceleration, rotational acceleration, and gravity, and shows that you can balance them, which means that the
What?
gravitational mass is the inertial mass.
Right. This is a very important point. I don't know if often did it cover it properly, right? What that force tells us is that m inertial is equal m gravity. Normally we don't think of that, right? M inertial is what appears in F equal ma, Newton's second law. It's really written here F mia. Mg is what appears in Newton's universal law of gravity, right? F is g m1 m2 over r squared. m1 g, m2 g. They do not have to be the same. Is that clear to you? That they don't have to be the same. Because, for example, in Coulomb's law, which is the analog to the gravity of the universal gravitational law of Newton, what appears? A charge, right? So in Coulomb's law, F Coulomb's, right, is Coulomb times Q1, Q2 over R squared, right? So that enables us to determine, how electromagnetic force acts on particles, right? Particles of similar masses, different charges will respond differently. Yes? We don't have that in gravity, right? We know that for electric force, some particles will be attracted, some particles will be repelled. In gravity, we don't have repel. All the particles are attracted. The same way. It is so important that it has a name. This is called the weak equivalence principle. If it says weak, that means that there is something which is even stronger than that. I'm not sure that you realize how important this experimental result is. We are now in a class. That is me. And there's desk here. And this is you. Chairs, right? This is you sitting in the chairs. What forces do you feel? I feel gravity. What else?
The normal force.
The normal force. That's enough for us. Now we're going to close the windows. We're going to close the windows. Right? No. Oh, okay. Imaginary. Not good. Imagine, of course. Okay. Now we're not in the classroom. This is Earth, right? This is Earth down below us, right?
Maybe closing the window
will help us, right? This is Earth here, right? Now we're not here. We're inside a spaceship. Which is, and the captain here, of course, right? Captain Kirk, right? And the captain puts on the engines. Now there are stars around us. We close the windows, we can't see, right? He puts on the engines of the ship. And what do the engines do? Accelerate. And let's say that acceleration A is equal to G. what are you going to feel?
The same thing.
Nothing. There is no way for you to know that we are not right now in a spaceship traveling somewhere out in space.
You're ignoring the fact that gravitation goes radial.
Yes,
Okay.
locally. You're right.
Also
Locally.
the centrifugal.
Yeah, Coriolis.
Coriolis.
Right. And, right. Locally. Locally. Right? Of course, right? You might have thought maybe of it, right? If you think of the alternative is to think of it as the elevator experiment, right? I showed you that, right? You have an elevator. You're inside an elevator, and the cable. You're a physicist. You're in an elevator in a huge building, right? Whatever Dubai, whatever tower they have there, right? And then the cable is being cut. What happens now? You freely fall. But no worries, there are some safety mechanism here that will stop you before you hit the ground. And as a physicist, of course, your main concern is to measure gravity, right? G, gravitational acceleration. How can you do that? The simple answer is you cannot. You're in a freely falling now. Simple answer is you cannot. To zeroth order. Now it's true, maybe I've showed you that as well, that because you're all attracted to the center of Earth, what you're going to feel in such a situation? Yeah, you'll see if you wait long enough, right, and this will go long enough, that you're getting closer to each other. Right, because you're all attracted, to the center of Earth, so you'll feel that. But that's a second order effect, small effect. Okay. Locally, there is no way to measure. Same here. So it's exactly the same thing, right? They just put us all in a spaceship. Now we're in a spaceship, accelerating spaceship. We try to measure, try to see if we feel anything. No, we don't. If we don't open the window, we look outside and say, hey, what's going on here? Can't tell. That is what Otmosh tells us. This is the true meaning of that experimental result, which is still ongoing. In a freely falling elevator, there is no way of measuring gravity to F0 order. Actually, the first order, second order correction. Okay. So, is that clear to everybody? It's physics here. It's a basic concept. Now, motivated by that, right? So this is a weak equivalent principle. It means there is a strong equivalent principle. What will be the strong equivalent principle was formulated by Einstein. He knew about that, of course, and he was motivated by that. And he formulated what's known as the strong equivalence principle, which, is not derived directly from that, but you cannot really think of any physical theory which will obey the weak equivalence principle, but not the strong equivalence principle. So the strong equivalence principle says what?
It's around every point you can create an initial. You can create around every point an initial reference frame.
Exactly. You can always find a freely falling frame locally. Right?
Freely falling meaning
you can always find a freely falling frame in which what? What is
Gravitation is zero.
Gravitation is zero. So what? What does it mean? That what? No. What does it mean?
Flat
Everything we said about special relativity holds in that system, locally. We did not waste our time. And the first few weeks of the semester was not a waste of time. So, strong equivalence principle. Strong equivalence. This is also what's called in short equivalence principles. When people speak about equivalence principle, it means strong equivalence principle. States that at every point in arbitrary gravitational field, it is possible to choose a locally inertial coordinate system such that within a sufficiently small region the laws of nature take the same form as in the unaccelerated Cartesian coordinate system. Which is essentially the same formulation of this really falling here, or that. Let's see it. Right? Basically,
isn't that just a first order approximation or zeroth order approximation? Isn't that just a zeroth of first order?
locally. I'm not talking about approximations. I'm talking locally.
Locally, meaning isn't just taking the gravitational field to the zeroth order, first order something?
No. It just means that the gravitational field can vary from point to point.
No, isn't just. I'm saying, isn't the equivalence principle just looking at the gravitational field and saying, okay, we'll take a zeroth order approximation of this specific point, and we'll be just local enough to.
No, you're missing something. What it says is that the importance is not that it's not local or global. The importance is that I can ignore gravity at all, locally. This is what's written here. That every place I have a gravitational field, I can treat it as not existence. Instead, I replace it with an acceleration. Alternatively, right, let's say this is Earth, right? We are in Africa, Europe, Asia, right? We're somewhere here. America here, right? Australia is here, right? Now, if we're here, somebody wants to do like a free parachute, how do you call it? Free diving, whatever, right?
Skydive.
Whatever, right? So there is somebody, skydive, right? So I can set up local inertial local coordinate system in which this guy here, right, does not feel gravity at all. In this system, right, he's a physicist, right? And physicists have some hobbies. He's going to do measurements while he's flying. He doesn't know that there is gravity. We don't measure it. It's really funny. Of course, somebody in Australia can do the same. It will be a different coordinate system. Right? Of course, the guy from Australia would fall the other way. So these systems are not the same, but both of them are locally inertial. Right? So of course, if you compare this system with this guy and this system with that guy, they won't be the same systems. That's the meaning of small enough region. If you have two guys right here, they may be able to use the same system. The importance here is not the local global. The importance is that I can ignore gravity at all. There is no gravity in this freely falling system. And I can proceed as what we did previously. Is that clear? Freely falling, he does not feel gravity. He doesn't know that there is gravity. If he waits long enough, he will know. But as long as they're still flying. Yes?
Does this mean local spatially or local both spatially and in time?
Space and time are connected, right? Forget about making this separation, which is completely arbitrary. We'll see that. More questions? Right. This itself suggests the fact that we have this and we have different systems. This by itself is enough to suggest that the effect of gravity is really to curve the space-time. The fact that I can put two locally inertial systems, but they are not the same at different points in space-time, means that what gravity really does is change the space-time from being Euclidean or Minkowskian to something which is more complicated. Okay? So, from here we get that the action of gravity should be attributed to the curvature of space-time. In reality, there is no such thing as an accelerated or globally inertial frame. Right? Newton believed in this absolute frame. There is no such thing. Why? Because there's enough that the universe contains one massive particle, one bit of energy, that will attract other particles. Right? So the only possible of having a flat space-time is for an empty universe, which is quite boring. And once the universe contains anything, that means that particles at different locations will be attracted to that something, whatever it is there, in different ways, meaning that there is no such thing as a global inertial frame. The only thing that we can think of is local inertial frames. So we focus on local inertial frames. That means that we need to think of ways of connecting the frame of this guy here to the frame of that guy here. Different frames. Should connect them somehow. We'll get to that shortly. Very interestingly, this already is enough to give you some testable prediction. Right? The testable prediction is called gravitational redshift. You've heard the point redshift. Right? Now, I don't know if you've noticed. There are, when people speak about redshift, they talk about two different independent effects. One is called cosmological redshift, which is associated with the expansion of the universe. Okay? We will speak about cosmology at the end. I decided that we are not going to skip that part. It's a really fun part. Talking about the Big Bang and all these things. And we will add, first I have to compensate for the lecture that we lost last week. But as needed, I'll add more lectures, just to make sure that we cover that. So you will know cosmology at the end. Introduction to cosmology. At the end, I will circulate, maybe on Thursday, I'll circulate paper where you tell me when we can add the lectures. So be here on Thursday and mark when we can add the lectures as needed. So one is called the cosmological redshift, is attributed to the expansion of the universe. Well, and we'll discuss it at the end. Dark matter, dark energy, things of that sort, which you heard of. We'll make some order. Second is what's called the gravitational redshift. Redshift due to gravity. We're going to develop it right now. So just make sure that pay attention. When we speak about redshift, we talk about different things. Gravitational redshift. Okay. So as usual, this is not working. As usual, we take the standard example. We have two observers in this classroom. Normally, of course, we call them Alice and Bob, but because we're in Israel, it will be Ayala and Benny. So Ayala try to change the bulb, which is not working. Benny is standing right here. Ayala wants to tell something to Benny. I love you, Benny, or more likely, bring me the hammer or whatever it means. How does she do it? What does she do?
She talks.
Physics.
Send a photo.
She sends a photon. Nothing is like sending a photon. So she sends him a photon. One. Then sends another photon. Two. Right? And I should mention that the separation, the distance between them is h. That's the height of the ladder. And of course they're on Earth, right? So there is a G here. Now, according to Ayala's frame, right, the two photons are separated by an interval, which we say delta tau Ayala. Right? This is the time difference, the interval between the two photons she sent. Benny receives these photons at the time interval, we call delta tau Benny. Now it's the same photons. They go through the same trajectory. Right? It's just photons. They don't do too much. Still, right, the equivalence principle implies that delta tau Ayala is larger than delta tau Benny. It's not going to be the same. Why is that?
Ayala feels weaker gravity than Benny.
Why?
Ayala feels weaker gravity than Benny.
Ayala is?
Feels weaker gravity because she's higher.
Yes, in a way, yes. Yes. So why is that implying that the photons, they go over the same trajectories? But why the trajectory? Why delta tau Benny is it's not the same as delta tau Ayala?
They don't have the same inertial frame if you want to convert them into an inertial frame.
Right. Right. Very good. Again, the way to think of it. Now Ayala and Benny are not, they are still in the room, but the room we said is inside the spaceship, and we have this Captain Kirk here, which instead of being in a G, right, is accelerating with A. Right? And so you can think of it the following. When Benny receives the photon of Ayala, he's already moving faster because of this acceleration. Yes.
Does this matter at which reference frame we measure H?
Of course it matters.
So why do we say H?
Right now it doesn't matter because we're just giving you to get the idea. When you make, of course, the distances change from frame to frame. Right now it doesn't matter. You'll see in a second. We're just going to cancel all the first, second, and third order terms. So I'm going to ignore. So let's do the calculation. The basic idea is that because of the acceleration, Benny receives the signals when he is moving at a faster rate than when they were emitted. Let's show that. Yes.
Is it equivalent to say that the photons are being accelerated down?
No, because photons travel at the same speed always. See, so you cannot really accelerate photons. You can give them energy or take away from them energy. But
Same speed you mean local.
what?
The speed is local.
C is always C.
Speed. The speed of
Yes. C is always C, regardless of what
but
frame.
the velocity of the photon.
Velocity of the photon is always C, regardless of which frame you look at. That Michelson Morley tells us. So you cannot really, I mean, it's a wrong physical term to say photon is accelerated. The correct term would say photon can gain energy and lose energy. You can think of it as accelerated, but it's better to talk in the right terms rather than confuse yourself and the others. Okay. So I'm going to neglect all these higher order terms. I'm going to neglect B over C squared. I'm going to neglect, we don't really care. Just means that also terms such as G, H over C squared, I'm going to neglect. So what we're going to do is good for first order, but that's good enough. So we're putting an axis, so this is the z-axis, right? So Bob's position, Benny's location, Benny's position. What is that? Is that Benny? Come on, there are no hidden things.
Squared
Right, half.
divided by 2.
half g t squared. My last position. Right. Now let's say the first photon was sent at t equal to 0. Right, remember, we talk about events. Remember that, right? So the first event is Ayala sends the first photon. This is the first event. Right? Now, it was received at time received at time t1. So the distance traveled by the photon is what?
Multiplied by
ZA at T0 minus ZB at T1 is equal to C T1. Because the photon travels at same speed c. Yeah? ZA T0 is H minus 1/2 G T1 squared is C T1. It's our first equation. Our second photon was emitted when? Said that delta tau Ayala. Second photon emitted at t equal delta tau Ayala. Received time
T1
delta tau. Received at t is equal to t1 plus delta tau Benny. So the distance it traveled Z Ayala at delta tau Ayala minus Z Benny at delta tau Benny is C times T1 plus delta tau Benny minus delta tau Ayala. Kindergarten. So, H plus 1/2 G delta tau Ayala squared minus 1/2 G T1 plus delta tau Benny squared.
Asaf, shouldn't be T1 plus delta T Benny in the ZB? ZB.
One labor.
Then B.
T1 plus delta tau plus kindergarten. So the same what's written here. So just expand. H minus 1/2 G T1 squared minus G T1 delta tau Benny plus 1/2 G delta tau Ayala squared minus delta tau Benny squared is equal to whatever T1 plus delta tau Benny minus delta tau Ayala.
Substitute first equation.
Yeah, now this is small, right? Here we have a delta tau squared, so delta tau is very small, so delta tau squared is very, very small, so I can simply get rid of that. And I can put here approximate because I got rid of that.
We can cancel out for the first
What?
equation. H minus GT1.
And of course, h minus half gt1 squared ct1. ct1, which measures that. So we're left with minus gt1 delta tau Benny is equal approximately c times delta tau Benny minus delta tau Ayala. Now T1, okay, I'll move it over there. Because here it will be. Now we have that T1 is approximately h over c. I don't need to go to higher orders. Everything with delta tau squared is I'm throwing away anyway. So we have here c delta tau Benny delta tau Benny c plus g h over c is equal to c delta tau Ayala divided by c. Build up that delta tau Benny is delta tau Ayala divided by 1 plus gh over c squared. Now I can use a Taylor expansion to write it as delta tau Ayala 1 minus gh over c squared. Delta tau Ayala is the time interval which between the times that the two photons were sent by Ayala. Delta tau Benny is the time interval between when the two photons were received by Benny. And as we see, these are not the same. This is shorter. We did that by assuming that they are, accelerating, but we said acceleration and gravity is the same. So the same thing will happen here on Earth. It's exactly the same thing. Now, just to make a small jump, what is GH? Gravitational potential, right? That's delta phi. So really, what is written here is delta tau Benny is delta tau Ayala 1 minus gravitational potential divided by c squared. So here, what we have is that the receiver is deeper in the gravitational potential. Actually, from here you can see the gravitational potential. He's down, she's up. It's deeper in the gravitational potential. Of course, if he tries to tell her something, it will be exactly the opposite. So, the received time will be slower than the emitted time if it's going up. And if we're talking about photons, they will get ready to get out of gravitational potential. Right? Because you can think of it as what's the difference between red and blue in photons? It's the wavelengths. First experiment that actually tested that was in 1959. It's called the Pond-Rebecca experiments. I hope I said the Pond-Rebecca experiment. Pond was the professor, Rebecca was a student. It was in Harvard. They just went up to one of the highest tower, and the highest tower that was in Harvard. And look at the emission lines from Iron 57. Measured. Of course, if it was not measured, then I would not tell you about the things. So we said similarly questions about it. Yeah.
If at Benny's floor there was a mirror and we reflecting the new photons out,
Yeah.
what is the relation between delta tau ILR and delta tau ILR the second time?
What do you think?
Should be same,
Really say.
but
Going down.
ILR has accelerated again and again.
What?
But relative to the, if you look at the spaceship, ILR has a different speed, and
The thing that you're referring to actually is, we'll discuss that too. Of course, she will see the same, if it's the same location gravitational field, she'll see the same energy. What will change, but you're right, will be the time. If you compare the time and you naively you neglect that, you just say, okay, the time should be h over c twice. That would be wrong. You get a different time because of this acceleration. That's called the Shapiro time delay. We'll talk about Shapiro time delay when we discuss properly.
Which is the next order.
What? No, it's not an S order. It's an exact. It's called the Shapiro. Yeah, actually, yes.
No.
It's an X. Yeah. Yeah. Shapiro time delay is a very small delay. It's a few microseconds on the scale of the solar system, but it's something which was measured in the 60s. Yes, but as far as the energy of the photon that she'll receive, it's the same energy if she's not moving in the gravitational potential. Yeah.
How could you approximate T1 to be H divided by C?
What's the problem?
You found the relation between T1 and H before.
Yeah.
So you neglected the T1 squared, but you don't know how small is T1.
Solve this equation. Okay. You know how to solve quadratic equation?
No, yes, but
Okay, solve this equation and tell me.
Only
Solve this
H is
equation.
small enough.
Solve this equation and tell me what's the fraction. Okay. And remember that I neglected things. Okay. I told you I neglected that thing. Okay.
But coming back to that again, if there's a difference, what happens to the equivalence? If there's a difference on measuring the bouncing back photons in a gravitational field, which the result is the same, and there's a difference if you measure it in an accelerated spaceship, what happens to the...
There's no difference. It's the same.
There's no difference.
There's no difference.
Okay.
It has to be the same. There's no difference. Okay? Guys, slowly. We'll decipher everything. Slowly. Right now, just get the idea. If you're in different location in gravitational potential, right? If one is deeper than the other in gravitational potential, the signal you're going to see, the time difference you're going to see is different. Same is true for photons. Right? Same is true if we're talking about the frequency of a signal, right? If you talk about photons, they have a certain frequency. So, if we have a light wave, light wave at frequency, ray I should say, nu, right? You can think of it as a crest of signals that are emitted. Right? Since nu goes delta t minus 1, delta tau minus 1. So if light is emitted at frequency nu star, that's what really happened, right? We are astronomers, we're looking at stars. Right? The star emits a photon, right? Some frequency, we call it nu star. Right? From the surface of the star. Of a star. That's what astronomers are looking at. Then it will be observed. It is observed at frequency nu infinity, namely infinitely away from the surface of the star. Now you're right, we're inside the gravitational potential of Earth. I can see in a second what's the difference it makes. Right, it's just nu star 1 minus delta phi over 6 squared. So it is really nu star minus gm over r c squared. M is the star of the mass of the star. R is the radius of the star. That means that the wavelengths lambda C over D increases. As it leaves the gravitational potential. Well, I'll tell you why. It means that it is shifted towards the red part of the spectrum. Yeah.
I don't know if it's physically makes sense, but is it the same equation as assuming that the photon has mass of E over C squared and just plug it in conservation of energy? You add just GM over R times the
I only talked about photons.
Why?
What? The mass is the gravitational potential. Or that you're asking? If I have if I have some potential made of photon ball or something, it will work. Yeah, it will be the same. Yeah, it's energy. It's a potential. What you really care about is the potential.
If the frequency goes inversely to the time difference, shouldn't the equation be opposite?
Yeah, it is. That's why you have.
No.
That's why. Yeah.
Alice emits the photons.
Maybe I'm missing something.
Alice emits the photons.
No, because Bob. Yeah, because here Bob is Benny is deeper in the gravitational potential. Here it's going from the star surface of the star outwards. That's the.
So
we have a star.
decide.
We have a star, and the photon is, the star is emitting radiation, and it goes from the potential well outward to us. We are somewhere at infinity. This is Ayala is sending a photon, and Benny is down inside the gravitational potential. That's why you have this minus. Here we have a photon that is emitted from the surface of the star and escapes to infinity to our telescope that we see. Okay, so don't get confused. That's why they look the same.
Maybe
The physical setup is the opposite. Okay, so just to give you some ideas, some numbers. So I made a small table with some numbers. So object, I don't know how many of you are astronomers or amateur astronomers. R in centimeters, mass in grams. So we're speaking CGS. And then GM over R C squared. So Earth. What's the radius of the Earth? 6 times 10 to the 8 centimeters. What's the mass of the Earth in grams? 6 times 10 to the 27. If you tell me in kilograms, we can convert it. It's not a big deal. And GM over RC squared, if you just plug in the numbers, you get something like 10 to the minus 9. So it's a very small correction. If I'm signaling somebody on the moon and I want to talk to them, I have some astronauts on the moon, I want to talk to them, it's a small correction. Where, by the way, it's very important? GPS. Sun, if we talk about a star like our sun, what's the radius of the sun, do you know? Roughly. Some idea. You did of course, what? Here, it's 10 to the 11 centimeters. What's the mass of the sun?
10 to the 2 to the
10 to the
2 times 10 to the
Million times the
33.
Good. Very good. That's correct. 2 times 10 to the 33 grams. What's the potential there? It's something like 10 to the minus 6. 1 part in 10 to the 6 is small, but you can see that. What about white dwarf? That you may not know. So the size of a white dwarf is something 10 to the 9 centimeters. It's not too different than the size of the Earth.
The mass is also
The mass is the same as the Sun. It's the 10 to the 33, roughly. Because it's much more radius, then the potential is 10 to the minus 4. That's getting more interesting. And the maximum we can expect is a neutron star. One star. Size of the neutron star is 10 to the 6. Below that centimeters.
like mass is the same.
Mass is the same, 10 to the 33. So the potential is 10 to the minus 1. That's a 10% difference. That's something which is very easy to use. So astronomers are seeing that routinely now for many years. Okay. Questions? That was the physics. Now we're going to go to the math. Okay. I'm going to dig into the math. You ready? It's very important the physics will be clear in your head because the math is going to be very confusing. So once you get confused, go back to the physics. Say, okay, that's what you're actually doing. Mathematical description of curved spacetime. Some parts are going to be a little bit ugly, I warn you. So with the example I just wrote and erased right now, right, we had two photons. They followed exactly the same path, yet the delta tau from the emission to the absorption was not the same. Right? We had the delta tau Ayala was different than delta tau Benny, and the reason is that space-time is curved. In the presence of gravity. It's curved in the presence of gravity. But we said, again, I'll put this small picture here, right? So we have, this is the Earth, and I have this guy here that is falling, and so it has a locally inertial coordinate system. Right. So, equivalence principle. Says that in a small enough region of space-time, the laws of physics are the same as in special relativity. Okay, so that's a good starting point. So I'm going to formulate, with this freely falling guy, right? There's a parachute here. So this is a freely falling system, freely falling coordinate system, which this guy is using. It's kind of helpful for him. So we're going to call these coordinates psi. Psi alpha. Not x, but psi. Those of you who are not familiar with Greek, I told you need to review your Greek knowledge of Greek alphabet. We're going to use pretty much all of it here. So these are the freely falling coordinate system. Psi alpha. So, what's the proper time?
What is
V tau squared.
so it's 1?
Oh,
Psi alpha, psi alpha.
thank you. Minus 1 over c squared. Right? Eta alpha beta. Psi alpha, psi beta. D psi alpha. D psi beta. There's a D here. What were you doing in the last 3 weeks here? Yes.
Isn't that letter zeta?
Maybe I'm confusing, but I call it
Psi
psi.
is another trail.
Yeah, there is another one. Yeah, you're right. Something like that. No, but I don't like it like that. I think it's no. Actually, no. I think. Yeah, you're right. Actually. You're right. Thank you. But, it should be like a 2 double here. But, I write it like that because I'm lazy. Right. Now, right, that you know. Now, if there is no force acting on a particle, what's the trajectory of a particle? Really falling? Yeah, how do we describe that? So, really falling particle. Right. What's the equation of motion of a freely falling particle?
X equal to Vt plus X2.
What is? Say 6.
Equal to Vt times.
What's the equation of motion of a freely falling particle?
V squared equals
A equal to 0.
2gm.
Guys, what were you doing here? What is the equation of motion of a freely falling particle?
x0 plus v
Good.
Half Vt squared.
We can close this. We can close this class. You're not listening to anything we say. What's the equation of motion of a freely falling particle?
Half Gt squared.
You're just making yourself
C
worse.
equal to 0.
What?
4 vector force.
Thank you.
equal to 0.
Which is given what? Write it down. du alpha over d tau is equal to d squared psi alpha over d tau squared is equal to 0. Guys, you're not going to get very far. I told you. I assume you know special relativity by now. Okay, this is the equation of motion for a freely falling particle, right? In special relativity. What is U alpha? I put a capital U. There's a reason to put a capital U. What is U alpha? What? D psi alpha over d tau. Okay. Now, you got annoyed by that. It took you way too long to say the correct answer. This was for a freely falling coordinate system, right? But I don't care about freely falling anymore. Now the coordinate system is not freely falling. So I'm going to use arbitrary coordinate system. Arbitrary coordinate system. So I'm going to call it X. Right? So it'll be X mu. It can be anything, note. It doesn't have to have accelerated, but it tends to be arbitrary, not a freely falling one. So now let's express express the proper time in arbitrary coordinate system. X mu. Now it's quite easy because I can simply use the chain rule. D tau squared is minus 1 over c squared. Okay. Eta is just a matrix. Okay. Remember what is eta. I trust you. Now I just have to express the old coordinate in terms of the new coordinates. Right? So d psi alpha over dx mu, dx mu, d psi beta over dx mu, dx mu. That looks a little bit ugly, so let's make it look nicer by writing it as minus 1 over c squared g mu nu dx mu dx mu, where g mu nu is defined as eta alpha beta d psi alpha over dx mu d psi beta over dx mu. What's the name of g mu nu? Yeah, this is the metric tensor. It has the same name as eta, but this is for any arbitrary coordinate system. Right? I did not say now anything about freely falling, not freely falling. I just say any coordinate system. This is the metric tensor. For arbitrary coordinate system. Which is what we're going to do. We're going to use. Now, what did we do? I'm just transforming coordinates. I'm not touching the physics. I'm just transforming coordinates the way I describe the physics. Yeah? Yeah. Now, so now I want to describe a freely falling particle. Right? Remember, in a freely falling motion, right, from the guy who's skydiving, what does he feel? Does he feel gravity? No, right? He just feels that, you know, everything, the world is very nice, right? From our perspective, here's it. It could be an astronaut, right, floating there in space and feel the same thing. He doesn't feel gravity. It could be somewhere on the way to Mars. Right? Now, if he's on Earth, right, what do we say? We do see acceleration, right? And we say that this is because of gravity, right? We see that it's accelerating. So how do we describe this acceleration mathematically? Well, let's see. So we now just have to take this equation of a freely falling particle and write it in the arbitrary coordinate systems. So let's do that. So in arbitrary coordinate system, a freely falling particle, does seem accelerated. Okay, so we take this equation of motion, write it down, du alpha over d tau. U alpha is d psi alpha over d tau. Now let's start again using the chain rule. Use the chain rule. So it's d over d tau. U alpha is d psi alpha over d tau. So I'm going to express that in terms of the new coordinate system. d psi alpha over dx mu over d tau. Okay, I want to express anything, and all the derivatives I want to express in terms of the new coordinate system, right? Right, it's clear what I'm doing here. So let's open it up, the d over d tau. So again, I have now two terms. So d over d tau of d psi alpha over dx mu, I write it down as d squared psi alpha over dx mu, and then dx mu over d tau. That's that term. Multiplied by dx mu over d tau. Note that here I have different coordinates, so I have to use partial derivative. Tau, there is only one, so I cannot be mistaken, so it's a full derivative. Right? Plus, here I have that, no problem, plus
Wait,
d
so y second term is
psi alpha over dx mu, d squared x mu over d tau squared. This is the derivative of that term. What's the question?
in the big brackets in the second term. Why this? Yeah. Why is dot tau and not d tau?
Because I was too fast. What did I do? Just change coordinates, that's all. Nothing alarming. Just looks ugly. So to make it look slightly nicer, we can multiply that equation is equal to 0, right? So we can multiply that by dx, whatever, lambda over d psi alpha, using the product rule, which is d psi alpha over dx mu, dx lambda over d psi alpha is equal to what? Delta of what?
Delta
Lambda mu. So I'm just multiplying here by that, and what we get, so this disappears. I have a delta. So we have a 0 is equal, this term gives us what? If I multiply this term, what do I get? D squared of what? X what? I have a delta lambda mu, so it's lambda over d tau squared, plus, now I have the second term. Okay, that's going to be ugly. These two I need, so I'm going to end up with what's called the gamma lambda mu dx mu over d tau dx mu over d tau. Gamma mu, lambda mu is defined as dx lambda over d psi alpha, d squared psi alpha over dx mu dx mu. Now this has a name. This is called the affine. Wait. This is called the affine connection. Fine. Yes.
Why don't you need lambda puts aside to the mu and u? Because
Oh, this is definition.
לא, כאילו, מבחינת אמרת שאסור לשים שני סימנים אחד מעל השני.
This is not a vector. Yeah. affine connection is not a vector and it's not a tangent, which is highly unfortunate. It's not. So it's written as a gamma, one upper index, two lower indexes, and one above, two others. Yeah.
How do you get from the second line to the third line? What? In the third line, lambda isn't set down the index, and the second line, mu, which is the...
I multiply by dx lambda over dx psi alpha. Right? Nothing here, right? This one, this and this gives delta lambda mu multiplied by d squared x mu over d tau squared. So this is just d squared x lambda d tau squared. Right? And here I have dx mu over d tau, dx mu over d tau, times whatever is left, which is dx lambda over d psi alpha, d squared psi alpha over dx mu dx. That's all. Algebra here is very simple. Yes. So we can also write that if we define the what is the x mu over the tau? U, right? This is the velocity in the new coordinates, x mu. So we can write this as, we erase that. So if we define mu, now it's a small mu, small u to discriminate from the capital U that we had previously. So u is defined u mu as dx mu over d tau. This equation can be written as d u lambda over d tau is equal to what? Minus gamma lambda mu nu, and then u mu u nu. What is this term now, physically? Acceleration. Right. Now when we look at the forward velocity of the particle from arbitrary frame, not a freely falling frame, what will that give us in a freely falling frame, by the way? Gamma? 0. In any arbitrary frame, right, this will be interpreted as acceleration. Hold it. Questions? Now I should just mention, so this is called the geodesic equation. And it describes the motion of a particle in any arbitrary frame. Now, we can repeat the same thing for massless particles. Right? What will be the difference if we do it for massless particles?
There's no tau.
Yeah, I cannot use tau. Then I can use any arbitrary frame, any arbitrary parameter to describe the motion of the photon. So for massless particles, right, and tau is replaced by something else, whatever, with sigma. Right, so we have du alpha over the sigma is d squared psi alpha over d sigma squared is equal to 0, and we write it down as 0 is equal minus g mu nu dx mu over the sigma dx nu over the sigma, or 0 is equal to d squared x lambda over d sigma squared plus gamma lambda mu nu dx mu over d sigma, dx mu over d sigma. Again, these equations, this and this, geodesic equations, they describe the motion of a free particle. There are no forces acting on the particle in arbitrary coordinate system. There's no physics here.
What do you mean like free particle?
What?
What do you mean like free particle?
There's no forces acting on the particle.
Oh.
It's free. Don't put any electric force, I don't put any. Again, in GR, gravity is not a force. This is just the motion of a particle in arbitrary coordinate system. That's all. Take a free particle. Think of some astronaut hanging somewhere out in the universe. Okay, not an astronaut, maybe some meteorite hanging somewhere out there in the universe. Right? Nothing, no forces act on that meteorite, but I can select whatever coordinates I want to. Okay. Again, this is purely math. Remember, we're not doing any physics now. We're just doing math. We'll connect it to the physics in a second. Well, maybe not today. Okay. Okay. Again, I emphasize it again. This calculation that we have here is entire math. It's pure math. It's got nothing to do with any physics. But we want to give physical interpretation. Basically, we said, okay, this is going to show us the gravitational acceleration. Right? So that in a way means that gamma is somehow would be associated with, or giving some interpretation of a gravitational force. Yeah, right? Although this is narrowing the mathematical definition, it's more than that. In this arbitrary frame that we choose, the proper time, d tau, was determined by g mu nu, right? The newly defined metric tensor. Which means that there should be some connection between this affine connection and the metric tensor. Right? In fact, there is a connection, which is, if you have any insight, it's quite difficult to assume that if you didn't see that before. And we get the metric, the affine connection can be derived from the metric tensor, and it's the first derivative. Okay, so in fact, it's the first derivative of the metric tensor that will determine the affine connection, which means something even more basic. I don't see that. Means something more basic. If this is gravitational force is derived from what? From?
Energy.
Force is derived from what?
Acceleration.
Potential. Potential. Okay. Go back to the first year, right? So it means that G, the matrix G in U, right, the metric tensor, essentially will be given interpretation of a gravitational potential. Because its derivative gives us the gravitational force, which is that. This is the acceleration due to gravity. But I'm putting some physical intuition, which we actually don't really need, just to give you the feeling of where we had it. Okay? You will need it, we don't need it now. I told you we're going to start digging deep. So what I'm going to do now, I'm going to start doing, and I'll do it even if it takes a few more minutes. I'm going to show you how I'm going to get to the affine connection from the metric tensor. It's a bit ugly. I know when it's ugly, it's ugly. I don't have. I'm not going to make it beautiful because I just say but you should know it. So let's just do it. The relation between the affine connection and the metric tensor. Okay, so we had the metric tensor G alpha G mu nu was beta alpha beta d psi alpha over dx mu d psi beta over dx. So I'm going to differentiate it. So dg mu nu over dx lambda is d squared psi alpha over dx mu dx lambda d psi beta over dx mu beta alpha beta plus d psi alpha over dx mu d squared psi beta over dx nu dx lambda at alpha beta. Annoying, but it makes sense. Now from the definition of the affine connection, I should have written it again. Gamma lambda mu nu is defined as dx lambda d psi alpha d squared psi alpha over dx mu dx. So from the definition of the affine connection, we have that d squared psi alpha over dx mu dx nu is gamma lambda mu nu d psi alpha over dx lambda. Basically, I'm taking the product rule here. See the idea. So let's use that. This is we get immediately from the definition. Let's use that, and we get dg mu nu over dx lambda is, okay, that's going to be here. Instead of mu, I'm going to write down. Let's start playing with dummy indexes now. Okay, so instead of lambda, I can put here a row. That doesn't change anything because I need the lambda here because I have a mu, then I put a lambda. Lambda and the lambda. I can do that because it's all dumb indices, right? Or because I use the same indices on both sides of the equation. So I have gamma rho mu lambda d psi alpha over dx rho d psi beta over dx nu beta alpha beta. This I just copied. Yeah?
This only applies when eta alpha beta is constant.
Eta alpha beta is constant. Eta alpha beta is eta alpha beta. We defined it. Eta alpha beta is constant. We know what it is.
But if we do the reverse transformation, don't get. We can't
no. Eta alpha beta. The definition is fully clear. I'm not.
Yes.
Eta alpha beta is just this -1 plus 1. That's it.
I'm saying that if we do the.
I'm not touching. Eta is well defined. Everything is well defined. I'm not touching the definition. The definition are not. Once I define it, it's there. It's fixed. Plus here we have d psi alpha over dx mu. So here again, I'm going to write it down as, rather than mu, I'm going to need a nu. So I'm going to change that to a nu. nu. So it's gamma rho lambda mu
Wait,
nu
these are not
lambda.
sheet.
Wait, dxi alpha over dx nu, and the d, this is a beta now, d psi beta over dx nu, eta alpha beta. But I have to follow the algebra quite closely. What's the problem? I just changed the indices. When I have the same index, I can do that.
I think you're missing the whole.
I don't think so. Nope. Ah, sorry, yes, you're right. This is wrong. You are right. Yeah, I'm good. Thank you. So I have a gamma rho lambda mu, and this is what's written here is just g rho mu, and here I have a gamma rho plus gamma rho lambda mu. By the way, from the definition of the affine connection, you can see that if I switch mu and nu, I get the same. So gamma lambda mu is the same as gamma lambda mu. I can exchange all of the last two indices. It does not affect the results. G rho mu. Okay. So now, we have this equation now. dg mu nu dx lambda is equal to that. Now I'm adding the same equation, but now starts exchanging indices. A lot of indices that I can now exchange. So add the same with mu and lambda, and subtract the same with nu and lambda. So we have dg mu nu over dx lambda plus dg lambda nu over dx mu minus dg mu lambda over dx mu. Okay, we're just adding the same equation with mu and lambda exchange and subtracting the same equation with lambda and nu exchange. And I get, so this is, okay, now I can't use rho anymore. I can, but I don't want to. So I'll write it with a kappa. So gamma kappa lambda mu g kappa nu minus plus gamma kappa lambda nu g kappa mu plus gamma kappa lambda nu, exchange lambda mu so I don't care, g kappa nu plus lambda kappa mu nu g kappa lambda minus gamma kappa mu nu g kappa lambda minus gamma kappa lambda nu g kappa mu. Check that I did not confuse any of the indices. That's part of the reason why I have to do these things very, very slowly at home. And this one will go with that one. That one will go with that one. And we're left with 2 gamma kappa lambda mu g kappa mu. So we're nearly there. What is left is to define the inverse matrix G with 2 upper indices as G nu sigma G nu kappa is delta sigma kappa. It's the inverse metric. Metric is defined like that. So delta function as expected. And then we take this equation that we left here, multiply that by 1/2 of the inverse metric G nu sigma. Yeah, and then we have the delta here, so everything is fixed. We have a delta kappa sigma, so what we have is gamma moving here. What we have, maybe I should be moving up here so that you see. And what we're left is with gamma sigma lambda mu is 1/2 inverse metric G mu sigma dg mu over dx lambda plus dg lambda nu over dx mu minus dg mu lambda over dx. Which is what I promised you. Once we know the metric, we can take its first derivative and the index, and we get the affine connection. Now, written in this term, the affine connection has another name. It's called the Christoffel symbol. Did any of you encounter that? Where? Geometry. Differential geometry. So this is called the Christoffel symbol. Symbol. And is also denoted with curly brackets. This is sigma lambda mu. Okay. What is it? If you encounter that, what is it used for?
Calculating curvature?
What?
Calculating.
We'll get the curvature, but right now we didn't calculate curvature. What is it used for? Why it's called the affine connection? People didn't show it to you in differential geometry? We're doing half a job. But what are we using it for? What is it connecting?
Moving vectors between.
Essentially, yes. It's connecting because the space-time is curved, but locally in different ways. Right? It's not the same curvature in each location, right? Remember, the guy free-falling in Australia and free-falling in Israel, they don't have the same, they have the same local free-falling, but they're not globally, it's not the same, right? If you want to connect between them, that's what you're going to use. We'll get to that. Okay, now remember, all we're doing here is completely mathematical. We started from a freely falling particle with a freely falling coordinate system. We said, how would we describe this free motion particle in any arbitrary coordinate system? It's a completely general. So I can use it for whatever I want. For example, non-Cartesian Euclidean spaces, I can also use it, right? So I can use it, since I can use it for any space, for example, this will be given one of the homework, but not the one that I already posted. Right, so this will be the last thing because I'm taking a little bit extra time, but I think it's important to finish with that. Right? For example, 2D flat space, flat Euclidean space, but I want to write it in not Cartesian coordinates, for example, in r theta coordinates. The prescription I was just given to you will work the same way. It's completely general. What is G? What's a line length element? ds squared. What? Right. dr squared plus r squared d theta squared. Right? So what is the metric tensor? G mu nu. 1, 0, 0, r squared. And I can use exactly the same prescription, right? You can see it from here, right? 1 and r squared, and there is no cross terms, the r d theta. What's the inverse metric?
1, 0, 0, 1 over r squared.
Right, 1, 0, 0, 1 over r squared. You actually know that, but nobody told it to you. So the only non-zero components of the affine connection, in this case, this is something which you can easily calculate, are gamma r theta theta is minus r, and gamma theta r theta, which is gamma theta theta r is 1 over r. Do and calculate that. You have the entire prescription here. Okay? I told you it's going to get slightly rough, but at the end of the day, you've seen it before. Just nobody told you. This is the mathematical prescription of what we have here. To be continued on Thursday. Do you have any questions? It's not that bad yet. Make sure that you understand what we're talking about. Okay, Krasky, what is the question of motion of freely falling particle in special activity? You're supposed to know the answer to that by now. How was the homework? How did you manage with the homework? What? It's the only homework that you had so far. It was fine? Okay. Was it helpful? I told you. We're not playing games here, right? We have to do these things. Otherwise, you're not very far from not understanding anything I said. Just make sure that you're following every single piece here, because the mathematics is very, very fair. But you have to follow. See you on Thursday. Second problem set is already. Just do it.
אתה רואה את דור במקום לראות את הנור.
שמע.